about Shinye? No? Okay, Chloe? Chloe. What about Ema? Okay. Emily? Oh, okay. What is this? Janine? That's how you read it, right? No? Janine is here? Okay. What about Justine? Like Kimberly? Maria? Another Maria. Is that okay? Maria, Nuruddin, no? Alif, Muhammad Alif, no? Najla? No, Najla? Can you? Ochi Siam, right? Sidra, right here. And then Yune. No Yune. Okay. Jinyan. Oh, perfect. Christian. Okay. Ushwa. Ushwa, anyone? No? And then Yiteng. No? And Wong Chike. Oh, perfect. Alright. So I hope you know by now this website, which is eLearn. Alright? So you will see your courses here. And in here, you can go to any course, whichever class that you are attending. You will go to content session where you will find these things, like lecture slides or whatever that your lecturer has uploaded there. So for me, I will upload all the lecture slides in this folder, which is called lecture slides. You will go in there, and there you will have your lecture slides before the class commences. So I try that I put in the lecture slides at least one day in advance for the class. If someone who is like super efficient and wants to go through the slides earlier, more than welcome, right? If not, then we will have the slides from here and they will be there, so whenever you want to go through them, more than welcome. How about my volume? Can you all hear me at the back, or do I need to be here? You can hear me perfectly? Right? So welcome everyone. Let's begin the proceeding of our chapter 1 and course Introduction to Organic Chemistry, aka Basic Biochemistry, without any further ado. So this is me without the long hair. Yeah, so probably I should have put longer hair picture here. But yeah, this is a good representation that I may look like this or like that. Right? My name is Dr. Ayaz Anwar. I have done my PhD in organic chemistry. I serve in the Department of Biological Sciences as an associate professor. My research expertise are in nanomedicine, medicinal chemistry, and discovery of antimicrobial agents. So they may sound a bit of mouthful at the moment, but when you will stay here for 3 years, I'm sure that you will get enough exposure with every one of these fields and more of them, so you will know exactly what are these. For now, they are just fancy names, probably, right? So the focus of my research is free-living amoebae, grain-eating amoeba, biomedical applications of nanomaterials, and natural products. They have hardly anything to do with organic chemistry except for natural products. So we will see probably later today or tomorrow that what natural products are and what brain-eating amoeba is and what free-living amoeba is, because I cannot help myself not talking about that. These are my research expertise and I only do research in these fields. So I have a few years of experience teaching organic chemistry. like 10 years until now. Do not be deceived by my young looks. Yeah, I did my PhD in 2016, and ever since I have been teaching different subjects, and organic chemistry, of course, is my core competency. In terms of research, I have published around 100 articles. I work in multidisciplinary projects within Malaysia, within Sunway University, as well as in international collaborations. This would be my only email address where you will correspond with me. You may find other email address for me, but this will be the one where I will respond to you. Right? Probably from my articles, you will see another email address. Or from different websites, you may find my other email IDs. But I recommend you to take a picture of this slide and feel free to reach out to me via email, as well as my phone number is there. So post-COVID, what I recommend is that you can make a WhatsApp group probably. Do you have a class representative yet? Not yet? Oh, so we have them? Oh, perfect. So can you please probably make a WhatsApp group and then pass the link to me? I will upload that on either, and then everyone can join me. So this would, the WhatsApp mode of communication would be somewhat not so formal, right? So if you have any questions anytime, of course, humanly possible times, not like 2 a.m. or 4 a.m. or something like that, like office hours or slightly later is fine. So you can put in there. But for any formal queries, this would be the email address, right? I am one of the lecturer which will be teaching you this subject, and the other half of this subject will be taught by someone else, whom I will introduce in a while, very, very properly. Yeah? So what will we do in this course? This is what we call our class learning objectives. So we have about 3 main class learning objectives from this subject and module. First of all, we will try to introduce you with some background and importance of organic chemistry or basic biochemistry. We will review some basic concepts from general chemistry today that are essential for success in organic chemistry. So organic chemistry is a type of chemistry which is built on many different things. General chemistry is also one of them. So today class will be basically an overview or introduction about things. We will hardly touch any important stuff today, but it does not mean that the things that we will discuss today will not come useful in our future lectures. Yeah? Beside that, we will study the types of structural formula which are commonly used in organic chemistry and identify isomers and explain the differences between them. Okay? So this will be your outline or the timeline for this subject. I have also uploaded this on eLearn. Yeah? So here you have a breakdown of topics and sessions, when your tutorials will be, when you will not have any tutorials, when your practicals will be, and when you will not have any practicals. So from this slide, you would be able to tell clearly. So week 1, where we are today, you only have lecture and lecture 1, which we are doing right now, which is Introduction to Organic Chemistry, History Applications. Week 2, only lecture, and this will be the topic. In week 3, we will have lecture 3, tutorial 1, and practical 1. Right? So your practicals and tutorials will only begin from week 3. While the mode of your teaching will be predominantly physical, because that's the MTA requirement nowadays, at least 70% of the whole teaching must be physical. Right? Of course, we will have a chance to decide later in whatever day, for example, public holiday falls in some of the classes or something. Then we can discuss on our WhatsApp group to decide otherwise that, well, can we do probably online session this week or that week. So this will be open to discussion once we will have that discussion for it. Is this understood? I have already had a few queries about the mode of classes. So until otherwise stated, all teaching would be predominantly physical. Yeah? And week 1 and week 2, no tutorials and no practicals. While in week 3, we will have lecture, tutorial, as well as your practicals. Week 4, again, same, all 3 things. Week 5, same things again. Week 6 would be the first assessment for you guys. So when we talk about assessments, that means the overall marks and distribution of things about this course. So this course is 4 credit hours, meaning that you will have 100 points altogether in this course. 60 marks will be for your final exam, right? And 40 marks will be for your coursework. And your coursework will be divided into 2 major aspects. Number 1 is your lab reports, right? So those lab reports will weigh 25% marks, right? So 60 and 25 is 85. The remaining 15% will be for your presentation, right? And when that presentation will be in week 13. And when your lab reports will be in week 6 and week 11. Why they are placed in 2 different places, I will get to it. But for now, you can just note down these weeks. These are very important weeks where you will be handing in your assignments or coursework, which are lab reports, number 1, and number 2, your presentations. Any questions so far, or am I going too fast? I can slow down a little bit if that's what you'd like. So can someone tell me how many marks this course carried? Alright, I wish that my hearing was this strong. Feel free to speak up. This is collaborative learning. I would not scold you or anything. I'm very friendly. At least that's what I'd like to say. Right? So yeah, speak up whenever you feel like. There's no place or time for you to ask questions or speak. So feel free. You can, change places, or we are not, I mean, personally, I'm not too big on discipline. As long as you enjoy your learning, I'm okay. You can do whatever you feel like. So how many marks again, class? 100, perfect. Your exam will be when?
14.
I didn't tell you this, right? So this was a trick question. When you will be having your presentations, how many marks your presentation will be?
15.
15, that's perfect, right? And as far as your lab reports are concerned, they carry how many marks? 25. So let me tell you this, if you would like to know this now, ideally, okay. If you forget about this, that's also fine, because we'll have proper time to discuss about practicals later. But you will have 5 practicals in this course, and each practical will carry 5 marks. So 5 times 5 will be 25, right? So you will notice this, that your first lab report submission is in week 6. That's after 3 practicals. So 15 marks will be covered in this submission. And then the rest of the 10 marks will be covered in this week, and which is also placed after 2 other practicals. Does this make sense? So first we will do 3 practicals, and then you will submit 1 lab report for all these 3 practicals. And that lab report will contain 15 marks. And then you will go with these 2 practicals, and then you will submit this lab report, which will carry 10 marks. So altogether, this is 1 coursework, but split into 2 parts. So one part is first 3 practicals, and the other part is last 2 practicals. Does it make sense? And then your exam would be, of course, after week 14, when you will have your proper timetable, probably in week 15 or 16. That's where you will generally have all other exams, including this one. Right? So now would be the perfect time when I invite the other co-lecturer for this course. So may I please invite Dr. Allen on the stage.
Dr. Allen. So yeah, I'll be co-teach with Dr. Anyas.
starting in week 9. Nice meeting you all. Thank you.
Right, so as Dr. Allen said, the first half of the course you will see me more, but it doesn't mean that you cannot disturb and bug him. That's why I gave his email ID and number here. Feel free to include him in our WhatsApp group or email group, or as you would like to communicate with each other and myself, as well as with him. While the other half of the course, starting from week 8 actually, that will be semester break, but yeah, properly you will be seeing him regularly from week 9. So that's how he looks like. Right? Any questions? This is the end of, the introduction and what this course is about, how you will be assessed, and all these things. From next slides onwards, we will talk heavily about chemistry. So any questions? Whatever is not clear, or there's something you would like to know, now would be a perfect time. Everything okay? Would you like to take a break or something? What? You're already tired? So that's what I like to do. I would break the lecture in at least 2 breaks. But those breaks will be very crisp, like 3 minutes break or maximum 5 minutes break. While in the meantime, when we will be studying, you will have some exercises as well on these slides. So every now and then I will say, well, now you need to solve this exercise, or at least try doing it. And then I will be sitting here and probably monitoring you to do it. So you will have proper break. It will not be like 2 hours one-way communication. That's what I want to tell you. So everyone okay? You probably would like to just finish this as soon as possible and be back home, right? So let's start the proceeding of this course properly. So the history and definition of organic chemistry starts with vital force theory. Oh, I forgot to ask a very important question. Is there anyone in this class who has never studied chemistry? Or organic chemistry? Everyone has studied organic chemistry before, right? Alright, then see you in exam. Take care. My job here is done. Right? Alright, so vital force theory you probably would know. Right? Anyone would like to take a dig on it? No? Right. Never mind. This is old school anyway. So before like 1800 something, people used to think that organic chemistry only deals with chemicals which are formed by living organisms. That's why the name organic chemistry. Right? So this was the principle before, when people were able to synthesize something by themselves, and which was called an organic compound. By the way, do you know what organic chemistry is? Right? So organic chemistry, technically speaking, is chemistry of carbon compounds. Carbon is one of the elements, you know, right? Do you know another element? Right, nitrogen, yeah, so all these are elements, right? Oxygen, hydrogen, calcium, blah, blah, blah. The periodic table, remember? The funny, colorful picture on chemistry books, right? So those are elements, and one of those elements is carbon. Carbon has an atomic number 6, an atomic mass 12. In organic chemistry, we deal with compounds which are made up of carbon. There are a few exceptions here and there. I wouldn't want to bore you with them, but if you'd like to know them, those are carbonates and bicarbonates and monoxides and oxides of carbon. So those are not included in organic chemistry. Other than that, most of carbon compounds are somewhat studied in a branch of chemistry which is called organic chemistry. So as the name suggests, that people like to think that organic compounds can only be prepared by living organisms. So that was called the vital force theory. but this was disproved in some 1828 by a very brilliant German scientist, Wohler. Wohler accidentally synthesized a compound called urea from an inorganic compound, which is ammonium cyanate. So when he accidentally put ammonium cyanate on heater, he found the crystals of a new compound, and upon investigation it was found that it was urea. And urea is an organic compound, so this disproves the vital force theory that organic compounds can also be man-made. They can be synthesized or they can be obtained from non-natural sources as well. So that is kind of the history of organic chemistry, how it came into being, what it was called, what it was considered before. But post Wohler, now the major definition of organic chemistry is there, that organic chemistry is what? The study of structure, nomenclature, and properties of carbon-containing compounds. Well, the exceptions are there: carbides, carbonates, cyanides, oxides. These are generally not included in organic chemistry. So do you wonder why these are not included there? Why this family of compounds is so exclusive and you only need a special pass or ticket to enter this club? Any idea? Right? You would think that, once you are saying that organic compounds are carbon compounds, then these are pretty much carbon compounds. You know what cyanide is? Right? It's carbon, triple bond, nitrogen. Yeah, C, yeah, perfect. You know what carbonate is? CO3. What carbide is? Just C itself. So these are the compounds where carbon is not bonded with other carbons by covalent bonding. So covalent bonding is also one of the conditions for compounds to be considered as organic compounds. So if you don't know what covalent bonding is, don't worry. Today's lecture is about these things. So we will see what covalent bonding and other type of bonding is. Right. So everyone know now what organic chemistry is? And you know why some of the compounds are not included in organic compounds? Correct? Let's look at some of the examples of organic compounds before we actually talk about different types of bondings. So these are the periodic table and periodic table of elements that I was talking previously. So you see here that some of the elements are in green color, some of them are in red color, and then some of them don't have their symbols in them. So this periodic table is actually the periodic table for organic compounds exclusively. So organic compounds will generally only have these elements. And the green ones are the ones which are there in almost 95% of organic compounds. While red and yellow, I think, is it? I am partial to colors. So yellow or brown? Right, so you are also partial to colors. Right, so somewhere in organic compounds you will see some of these elements, but mainly like 95-98% of organic molecules will only have 2 to 4 elements, which are these green colors: carbon, hydrogen, nitrogen, oxygen. That's all, these 4 elements. Do you have any idea that how many organic compounds would be there in the world? Because you see that there are so many elements which are not included in organic compounds. So only few elements are covered in organic compounds, right? So there would be very few. Correct? No? Okay, let me rephrase my question. So these are the elements for organic chemistry, right? The other elements would be the element of inorganic chemistry, right? And then most of the elements are actually participating in inorganic compounds. So do you think that in this world we have more organic compounds or we we have more inorganic compounds? Based on this chart, it appears that you would have more inorganic compounds, right? But that's not actually true. We have roughly in this world around 10 to 12 million organic compounds and only 5 to 4 million inorganic compounds. And the reason for having so many organic compounds is the ability of carbon to bond with itself. Not many other elements can bond with itself. They need a suitable partner to make a suitable bond. But carbon, on the other hand, has this ability that it can form many different structural bonds with other carbons. And that ability is called catenation. You would have heard this term before, no? So C-A-T-E-N-A-T-I-O-N, catenation. So catenation is the property of carbon by which it can form bonds with carbon itself. Yeah? And then there are actually more organic compounds in this world than there are any inorganic compounds. So at this point of our class, I generally ask this question. Can you all look around in this room and give me an example of what do you think is an organic compound? Cellulose. Where do you see cellulose? In the door. Door is made up of wood, and wood is cellulose, and cellulose is indeed an organic compound. Very good. Any other example? What do you see around? The seats where you are sitting is made up of what? Plastic, foam, fabric. All of these are organic compounds. Right, now give me one example of inorganic compound in this room. By the way, we ourselves are, all together many organic compounds. Right? The skin, blood, so many things, they carry so many organic compounds. Yeah, so inorganic compounds. Do you see anything inorganic is in this room? Light? The bulb. Diode. You mean the metal diode? Right? Yeah, metals are basically inorganic. So, good guess. What about oxygen? Oxygen is in this room, right? It does not have any carbon. So, inorganic, right? What about nitrogen? All mainly gases are somewhat not organic because they don't carry carbon. And of course, metals. So wherever you see metals like aluminum, or so metal there probably in your speakers somewhere, those would be the examples of inorganic compounds. All right. So I guess you have the idea now. Okay. Yes. Iron mainly is not included in most of the organic compounds. Probably very few compounds which contain iron. So these these elements are the ones which are generally found in organic compounds. That's the only reason. So this is kind of the periodic table for organic chemistry. Yeah? Right, so out of all these 10 million, 12 million organic compounds, these are a few examples which I would like to probably think of. Personally, I love these molecules because of their utility, how simple they look, but how practical their applications are. For example, DNA, right? So DNA is part organic compound. It contains all those A, T, C, G. Those are basically organic bases. Yeah? And then you have isooctane or any sort of petroleum compound. Petroleum is I mean, people are changing their source of energy to renewable energies in electric vehicles and everything. But even then, a lot of the world depends on petroleum products, right? So one of the example I've put here is called isooctane, which is added in the petroleum, the gasoline that we put in car. We call petrol here, right? Not gasoline. Well, what do you fill in cars? Petrol, okay, petrol. Yeah, so petrol is basically a mixture of alkane compounds like hexane, heptane, octane. That is petrol. So in petrol, we also add this compound, which prevents the engine for knocking. So this is one of the anti-knocking agents. You know what knocking is, right? That when your engine does not smoothly run, you will hear the noise in the exhaust of the car. So that's knocking. So to prevent knocking, we can add isooctane compound. So the petrol we put in our car, it already contains it. If it doesn't, then in some countries people manually add that as well. This example is of a compound called cis-retinal. So this is found in the retina of the eye, which helps you in identifying colors. Right? This is neurotransmitter serotonin, very small, cute-looking molecule, right? Not very toxic, not very complex. That's what I mean. But this is essential for all the movements that we make. Serotonin actually dictates if you want to move your hand up or down, or shake your leg or whatever. So some examples to tell you the importance of organic compounds. Of course, there are like millions of compounds, as I say. So use your imagination to think of the applications of organic compounds. Yeah? Where organic compounds are generally utilized, what are the common applications of organic chemistry? So there you have it. Organic chemistry is widely used in energy sector, as we were just discussing now, right? Petrol and these things. Medicine, most of the drugs that we take, most of the compounds, preventive compounds, those are basically organic molecules. Many aspects of organic chemistry are involved in environmental pollution, as well as how to tackle those environmental pollution. So in environmental sciences, a lot of organic chemistry and organic compounds applications are utilized. Chemical biology, DNA, RNA, all these things. Yeah. Catalysis, asymmetric catalysis is a fancy word for synthetic organic chemistry, basically. So when you want to synthesize newer organic compounds or drugs for any newer applications, you would use synthetic routes to prepare new compounds from probably previously known compounds, or from scratch. That depends on what you are making. So that is generally covered in asymmetric catalysis or synthesis. And then natural products are organic compounds which, as the name suggests, are still obtained from natural resources. Yeah? So all of these are some of the areas where organic compounds can be found as driving force in those industries and well as in those applications. Yeah? So from my heart, I am not forcing you to give them a round of applause, but how boring the life would be without chemistry. We would not be able to see colors, we will not be able to taste so many things, we will not be able to smell so many different smells actually. Do you think that the smell we get from perfumes, what are those compounds? Esters, mainly. Organic compounds again. And how do we differentiate between different smells? Our nose also has receptors to accept those compounds. And then with those receptors we can tell that if this fragrance is sweeter or fruitier or woody or whatever. So all these details, it comes from these organic compounds. Yeah? Alright, so with that, let's revise some of the previous things that we have studied in general chemistry. And why we are revising these? Because You will hear these things in every lecture here and there, every now and then. So since today's lecture is all about overview and background, so from here onwards, we will revise some of the concepts which I am sure that you have studied before in your general chemistry. But if you feel that you don't know them, I will not judge you. There is no silly question, there are only silly answers. Right? So whatever you feel like that you don't know, you can raise your hand and we will go in a little bit more details of that. Of course, we cannot and we will not be able to go in a lot of the depths of these topics because they are not basically in organic chemistry. So do you get my idea? Right? But please do not feel hesitant. If you have any question you cannot remember or that if you ever studied these topics or no, just feel free to raise your hand, yeah? So you have some idea about the structure of atoms, right? There are many theories and principles about explanation of atomic structure. You remember Bohr's name, Rutherford's name, putting electronegativity, all these things, yeah? So we will not cover all those. I will just give you the idea of what atomic structure looks like. So we have some positive nucleus in the middle, and then the electronic density is at the edges of the structure of atom. The most area or volume of the atoms is actually empty because nucleus is very small and it's in the middle, and then electrons are also very small, but they are rotating somewhere around the nucleus based on the electrostatic and centrifugal forces. Yeah? And then a lot of details, I guess we can just skip them. Isotopes. It rings a bell, right? Anyone who has not heard this name before? Right. I will pretend like I have not heard this before. So anyone else? Everyone have heard the name isotope before, right? This is not a trick question, by the way. And then you will not be, losing any points if you don't know, because this is just a lecture. We are all here to learn, so please do not feel shy. Yeah? So isotopes, by definition, are the elements which have same atomic number but different mass number, right? Or same number of electrons and different number of neutrons. These are the two definitions. Both have the similar impact on the overall things, but whatever you want to remember, you can remember any one of these. So same atomic number, different mass number, or same number of electrons and protons but different number of neutrons. So since we are dealing with carbon mainly, so the common isotopes of carbon are C12 and C13. So C12 is at the 99% abundance, and then C13 is at about 1% of abundance. Yeah? Right, so you have your definitions here. Right, so the next topic we need to review before we can actually start about organic compounds is electronic configurations. So anyone again, I will raise my hand, who have not heard this term before. So what is electronic configuration? Right, so probably I should ask you then. How about that? Right, maybe randomly picking. Right, so, oh, this is very broad. Alright, so somewhere here. Probably you, yes, the lady with the laptop. What would be your name? Alright. Do you know what electronic configuration is? Wrong answers also count, so yeah. valence electron somehow. It shows that you have studied this somewhere, probably not at the top of your mind at the moment, but yeah, thank you so much for taking part in this exercise. Right, so randomization number 2 then. How about you, lady? Yes. You can start with your name. Celine. Alright?
Electronic configurations is the arrangement of electrons in the orbital of
Wow, this is like perfect. Yeah, so it is a way by which we can arrange electrons in any element, right? So then you would remember orbits and orbitals and suborbitals, right? So orbits are where electrons are. Then there are like orbitals, like s orbital, p orbital, d orbital, and f orbital. You've heard their names before, right? You would remember their structure as well. S is round, and then dumbbell, and then double dumbbell, and those things. So those are orbitals. And then you have suborbitals, like S is just S, but for P you could have Px, Py, Pz, depending on what is their orientation in the space. So how do you fill the electrons in these orbitals is called electronic configuration. When we talk about electronic configurations, there are a few principles as well, like Aufbau principle, or Hund's rule, or Pauling electronegativity. Yeah? So probably it would be a good idea for you to get into this zone when we meet next time. But the important one which I would like you to remember are actually Hund's rule and Aufbau's rule. Yeah? So Aufbau's rule says that when you have to fill electrons in different orbitals, you will start with lower, orbitals in energy first, and then you go to the higher energy levels. Yeah? And then Hund's rule says that if there are two similar energy orbitals available, then the electrons would like to be unpaired first, and then later only if there are further electrons, they would like to be paired, because for pairing electrons, further energy is required. Electrons can have different spins, and to those spins to be aligned or disaligned, they will need extra energy, and if there is an option, they will not like to be paired at all. But when there is no further option, then with excess energy, they can be paired. Right? So this is what is told by Hund's rule, while Aufbau simply tells us that which orbital has lesser energy and which orbital has higher energy. Yeah? So do you remember some sort of this sequence, SSP, SP, SD? Like this is how I remember the sequence of energy. But yeah, there's a picture as well where we write. Probably I can show you here. What? Yeah, this one. You remember seeing these images, right? So this is how we can easily tell that which orbital has less energy and then which orbital has high energy. So if you need to fill electrons, you will start from here, and then there, then here, then here, then here, then here, then here, and it goes like that. Right? Okay. Yeah, so hydrogen only has one electron, it will go in 1s1. Helium has 2 electrons, so 1s2. S can only take 2, right? P can take, and then D can take, and then F. Perfect. Yeah, so this is how we simply fill them out. So when the third electron came, it went to 2s. Then S can take 2, so another can come here. Then the next will go in P, then Px, Py, Pz, and so on and so forth. Yeah? So important is carbon. For organic chemistry, the most important is carbon. If you can't remember for some reason all of them, try to remember the electronic configuration of carbon. It will be very useful. Yeah? Right, electronegativity. So, electronegativity is a force by which an element can pull a pair of electrons toward itself. This is inherent in different elements. Like, different humans have different strengths. So different elements have different electronegativities. So electronegativity, why this is important? Because the difference in electronegativity dictates what will be the type of bonding in a compound. Yeah? So generally speaking, you can see all the slide, right? Yes. Okay. So when the difference in electronegativity between two elements is more than 2, then it would be an ionic bond. So ionic bond rings a bell, where you will have proper creation of ions in a compound. Ions are the cations and anions, so positive and negative charges. So those are generated based on the differences in electronegativity. And when the difference in electronegativity between the combining atoms is big, then the bond will be ionic bond and you will have clear ions. But when it's less, like 0.5 or something like that, then that bond will be covalent bond. While covalent bond could also be differentiated between polar covalent bond and non-polar covalent bond, depending on, again, the difference of electronegativity. If the difference is very little, then it will be non-polar covalent bond. And if the difference is somewhat larger, then it will be polar covalent bond. So here is a range, but it's not very, black and white. Sometimes you will have gray area as well. So you will have to see clearly that what exactly is happening in terms of the difference of electronegativity. But the common examples would be, you take one metal and one non-metal, you get them together, so those will be clear indication of polar covalent bond or an ionic bond. Right? Any questions? Like lithium fluoride, sodium chloride, all these are polar molecules. Why? Because they have clear differences in the electronegativities of the elements which have made these bonds. But carbon and hydrogen, this is the most common bond that you will encounter in organic compounds. So there is not much difference in electronegativity, right? So this is a good example of a covalent bond. Right? Right. What happens in ionic bond? Because of so much difference, there's no sharing. One element can pull up the whole electron towards itself. Like in this case, fluorine has, attracted the whole pair from lithium. And therefore, we have clear charges on the molecule, plus, minus. So how would you tell that if compound is ionic? If it has a clear charge on it. If the elements which came together and made a bond, and there is no charge on the molecule form, then you could simply tell that this may be a covalent bond. But for a compound to have ionic bonding, you will see the clear presence of plus and minus charges. Make sense, right? Right, so covalent bond. Here we don't have clear winner, So both elements, they share the pair of electron which is involved in the bonding. Yeah. So in non-polar covalent bond, we will have somewhere in the middle, while in polar covalent bond, this shared pair could also be skewed towards one of the element based on their difference in electronegativity. Right? Make sense? So carbon and chlorine, for example, they have some difference in electronegativity, but not that much that you can, make those ions. So that's why polar covalent. While example of non-polar covalent would be somewhat like hydrogen and hydrogen, or the bonds between same atoms. Yeah. Right. So this is mid-hour. What do you think? Should we continue or take a quick 3 minutes break? Right? Alright, then we will resume at 6:03. Let's take 4 minutes.
Me on my way to the business management, I go to the office.
In the meantime, if someone's attendance was not marked, can probably come here and mark it yourself. Yeah? You can just come here and click on the green thing. For hybrid, then I can instruct anyone here? They would have this idea when you have, for example, for the hammer force, you don't have practical examples where you probably you will have for this course we will have practicals. You know where you sit? Or if you want, the general area where you will find some Miss Regina or Miss Natalie? So here, if it's here, then it's not in this, right?
Sorry. Thanks for it. It's hard to know.
Know where to find this. So everyone settled in already? Right. So the next topic is kind of important. I would take some time here with some examples because from here onwards we will talk about the structures of organic compounds. Yeah, so to build the structure of any compound, there are again many theories, many rules, and many principles. One of them is called Lewis structures or Lewis principles of making structures. So here is the detail. I will give you probably 1 minute to read this slide. That would be very helpful, trust me.
This is the one with the hand bracket. So
Right? Rings the bell? So these are some of the rules to make Lewis structure. We will look at them one by one with examples, so don't worry. But once you read it, you would have idea that yeah, you know this stuff, how to do this, how not to do this. So let's look at those examples, yeah? So CH4 is one of the examples. It is pretty much the most common organic compound. The name is methane. Yeah? Don't worry about it. We have a dedicated chapter for alkanes where we'll cover all the alkanes, but in future. Forget about the name. So this is the formula of compound CH4, right? So what you need to tell first that what are the elements? Carbon, and then there are 4 hydrogens. So carbon comes from group 4, so it will have 4 electrons, right? Hydrogen only has 1 electron, but we have 4 hydrogens, so altogether we have 4 electrons. So 4 plus 4 is 8 electrons, right? And octet is kind of important for Lewis structure because you read in the previous slide. So duet and octet are, according to Lewis, were the stable molecules. So all molecules would like to make octets if possible, right? So with that, we can simply rearrange the electrons in pair form and place them away from each other. So this is how you simply make the structure of, methane, right? Now, if you are asked this question in exam, and let's say that you put these CH groups close to each other, you might not get full points, right? So in chemistry, sometimes thing needs to be specified. So they must be placed maximum possibly away from each other. But Lewis is not about 3D structures, it's like 2D representation of structures. So it would be fine if you just make a plus sign like that. Okay? But now probably you would remember that all these compounds are actually 3D, which we will discuss in our next lecture. But for Lewis' point of view, this would be okay. But in any other way, if you draw them, for example, all CH you draw in one line, so you will not get full points. Right? Ammonia, nitrogen, 3 hydrogen, simple stuff, right? This is how you can make. But since there are only 3 hydrogens, so we can only make 3 bonds. So what happens with the unutilized electrons? So they stay there just like that. And we call them non-bonding electron pair or simply electron pair. Yeah? So what you see here, that every bond is actually an electron pair, isn't it? So this bond is formed between carbon and hydrogen when these two electrons paired with each other. So this is called a bond pair, and this is called a lone pair. Right? Correct me if I am wrong, or this is the first time that you are hearing it. You have heard these terms before, right? Bond pairs and lone pairs. Lone pairs are the ones which don't take part in the initial structure of the compound, while bond pairs are the ones where we get a new bond. For example, the NH and the CH, right? Water, another example, easy stuff, right? It only has two hydrogens, so we make two bond pairs, and then the rest of oxygen's electron, we have two lone pairs, correct? Chlorine, it has 14 electrons, but chlorine can only make one bond, so chlorine make one bond pair, and then each chlorine has three lone pairs, right? Correct? So if you get a question in exam that how many lone pairs are in chlorine molecule, so your answer should be 6. It shouldn't be 1, 2, 3 only, because the key word in the question was molecule, not atom, right? So be prepared for these tricky wording in the questions for your exam. Well, we will talk about exam in future, so don't worry about it. Most of the assessments we will cover in our tutorial session, yeah? But in lectures we will try to focus on theory more. Right, so these non-bonding electrons, also called lone pairs, here is the example. The bond pairs, you can simply represent them with a line. Line represents a bond, right? So between C and H, you see those lines. So these lines are actually bonds. 1 bond, 2 bond, 3 bond, 4 bonds. Carbon can generally make 4 bonds, right? Nitrogen can make 3 bonds. Oxygen can make 2 bonds. So this is very well known information, right? Right. Sometimes we can also have multiple bonds. Not only single bonds, but we can have double bonds or triple bonds as well. This depends on how many electrons are taking part in that bonding. So for example, here we have a double bond between C and O. How this happened? Because 2 electrons from carbon and 2 electrons from oxygen decided to interact with each other. In this case, again, a pair from each side came into contact with each other, and that's why we have the carbon-carbon double bond. Right? Right, so can you try probably drawing the structure of N2? This wouldn't take long at all.
Nitrogen. What's the valency on that? The outer shell.
I want you to draw Lewis structure, meaning that the electrons should be represented as those dots, as we just seen in previous slides. Yeah?
7. And here she could.
It's already given, right? Because nitrogen can make 3 bonds. Here we only have 1. Alright, so yeah, the answer is there as well. Right? Right, so I want you to attempt these questions in future so that, you will make use of your brain and you will get into the habit of solving things. Or this is something we can discuss, that should I not give the slides before class? So these are the pros and cons of both things. I put them before class so that if you have chance you can go through them. And then you will have better questions to ask. But the other way around is then you will have the solutions to the problems as well. Right, so we will need a bit of honesty from both sides. The only reason I want you to practice these is so that you also get involved. Otherwise, chemistry can be really, really sleepy as well. Right? So, yeah, we will discuss this once we have our discussion for a while. Right, so this is how the structure should be made. Nitrogen can make 3 bonds, so yeah, 3 bond pairs, and then only 2 lone pairs, just like that. Other example is ammonium. So ammonium ion has a plus charge. Plus charge would mean that you can take away an electron. A negative charge would mean that you can add up 1 electron. So this is how it should be written. Right? Let's move on to the next topic, which is dipole moment. Dipole moment is pretty much related to the bonding patterns. Right? So this is the physical force by which we can have, as the name suggests, the creation of poles in a molecule. Right? And this is pretty much mathematical and physically determined. Right? So by definition, this is the product of amount of charge separation multiplied by bond length. So bond length can be calculated using physical measures, instrumentations. Charge separation can be measured using calorimeter and other sort of meters. And once you have those two values, you can multiply them and you will have a mathematical figure. And that figure is called dipole moment. How this is represented? This is represented with the help of what we like to call an EPM, electrostatic potential map, where the red color represents high charge density and blue color represents low charge density. Yeah? So it's called EPM. So if you see pictures like this, you will know that they are trying to show us what is the density of electrons in this molecule. The red would represent what? With charge? Negative, because that's what electron carries. Correct? Right, the next thing I want you to probably brush your memory about is called formal charges. Sometimes we can have informal charges as well, probably. So there are no informal charges, there are practical charges or formal charges in a molecule. Right? So practical charges mean what exact charge molecule carries. Sometimes any element in a compound can have a formal charge as well, which is not a practical charge, but it is there for formalities. How we calculate that? There is this equation you need to probably memorize. I don't like memorizing things, and my memory is very weak. So wish you good luck in remembering this. Yeah? But yeah, this is how it goes. Formal charge equals to group number minus non-bonding electrons minus half of the shared electrons. So how do you get these values? All these values of group number, non-bonding electrons and shared electrons, you can get if you know how to draw the Lewis structure, which we just learned now. Right? So for any given question, you will just draw the Lewis structure, and from there you can tell that how many bond pairs are there and how many lone pairs are there. And then for group number, this is trivia. So for organic molecules, you need to memorize again that oxygen is from which group, nitrogen is from which group, carbon is from this group. Yeah? I'm sorry, there is no way around it. If there is, I would have told you. But I hate to memorize things. Which reminds me that if I don't respond to your emails in, say, 48 hours, you are allowed to text me or call me on my phone. Right? But give me around 24 hours at least. Because as I said, I'm very forgetful. My memory is getting thrown away out of the window. Yeah? Right, so here is an example of hydroxonium ion, which is H3O+. So we have drawn the Lewis structure, and then we are just putting these numbers in the equation to calculate the formal charge for any given element. So in question, the examiner should ask you that you need to calculate the formal charge for which element? For oxygen or for hydrogen? So in this case, we are calculating the formal charge for oxygen. So we will put the group number for oxygen, which is 6, right? Non-bonding electrons. How many non-bonding electrons it has? Only one pair, meaning 2. So here's your 2. Half came from equation. And then how many shared electrons do we have? We have 3 bonds, so each bond is made up of 2 electrons. So shared electrons are 6. So here we have 6. Once you solve this equation, you get +1. So that's the formal charge of oxygen. Does it make sense? Any confusion? Just for your record, there is another example of NO+, that is nitroxonium ion. This is the Lewis structure of nitroxonium ion. We have drawn it by ourselves because if you are asked in exam that give the formal charge of nitrogen or oxygen in nitroxonium ion, then you will have to draw the structure by yourself, right? And then in exam you will be asked that you need to calculate it for nitrogen or for oxygen. Yeah? So for nitrogen, here we go. We put all the numbers there. Nitrogen is from group 5. Then there is one lone pair, so 2, and then 3 bonds there, so 6 shared electrons. The formal charge of nitrogen is 0, and then on oxygen is +1. Right? Makes sense, right? Alright. Yeah, so this is kind of important. If you can't remember a lot of things, try to remember that you can remember this. This is kind of summary of important stuff that we do need to remember. So carbon has 4 valence electrons, nitrogen has 5, oxygen has 6, and halogen, group 7, they have 7 valence electrons, and these are also the group numbers of these elements. So they usually like to make these many bonds. So carbon makes 4 bonds, nitrogen makes 3 bonds, oxygen 2, and halogens they make 1. Then how many lone pairs they will have if they are utilizing all their resources? Then carbon will not have any lone pairs. Nitrogen will generally have 1 lone pair. Oxygen will have 2, and halogens will have 3. Right? Another important information, how they will look like in their common form and how they will look like in their not so common form. So for example, let's just only probably focus on carbon because that's what imperatively the most important one for us. So this is how you will see 4 bonds of carbon, but it can also have 3 carbons in both stages, in plus ion as well as in minus ion. So this is called carbanion, this is called carbocation. We will have these fancy names many times, or you can simply call them carbon positive ion and carbon negative ion. Easy, right? And why it's negative? Because it has a lone pair here. Why this is positive? Because there's no lone pair here. Despite that both of them only have 3 bonds as opposed to 4 bonds. Right? While when it's in 4 bonded form, there's no charge here. Correct? And the other examples are there. You can probably review them in your own time. Carbon is the most important one. Yeah? Right, so this is the part where generally I have questions from the class. I have not have any questions so far, which is a bit disappointing. So the reason that I am telling you that this is the part where I generally have questions is to encourage you to ask me questions as well. Yeah? So resonance forms are the structures which are interrelated to each other only by the movement of electrons. So imagine that you drew a Lewis structure of a compound, but then you realize that there could be another Lewis structure for the same compound as well. So those multiple Lewis structure of a possible one compound would be called Lewis structure, the resonance forms of each other. Why they are called resonance form of each other? Because you can interconvert them with each other only by moving a few electrons here and there. Okay? Let's look at the examples and then it will make a lot of sense. So once we have multiple structure of a same compound, how do we decide that which of them would be the correct structure of the compound? So in those cases, generally, if you put them in an X-ray crystallography machine, it will give you the structure which is intermediate between those two structures. That's why we like to call it a hybrid structure or a hybrid resonance form between two different structures. We will look at it from examples so it will make more sense. But the point is that once you have multiple options of making structures of the same compound, then the true structure or the accurate structure of that compound would be somewhere in the middle of those two compound structures. Right? So what I'm saying is this. So this is a compound example where somebody make a structure, there's a structure like this, without the pink arrow, of course. So there's nothing wrong with this structure, right? Every element has proper bond pair, lone pairs or whatever. But then somebody did not drew it like this. Another person drew it like that. Again, there's nothing wrong with this. Everything is being followed as per the instructions of Lewis, right? Instead, we have a carbon-nitrogen double bond here, while we have carbon-nitrogen single bond here. And how this single bond can be converted into double bond? Just by moving this pair of electrons. How and why we can move these electrons from nitrogen to carbon is because nitrogen has a lone pair, first thing to notice. And then second thing to notice is that the neighboring atom has a positive charge. So positive charge implies what? That it needs electron, right? So it needs electron and the neighboring atom has an electron pair which is just sitting there. So you can simply move this electron toward this direction, and once you do that, you will make a new bond, right? So these two are what we call the resonance structure of each other. And why are we calling them in resonance? Because they can resonate with each other by simple movement of electrons, as denoted by the pink arrow. Yes?
Is this something related to the principle of magnetic field?
MRI. So all the magnetic resonance imaging or nuclear magnetic resonance spectroscopy is done on the movement of electrons, yes. So the term resonance simply means interchangeable, where electrons can move. So MRI, nuclear magnetic resonance spectroscopy, all these things, they have something to do with the movement of electrons or other particles, not necessarily electrons, huh? Sometimes it could be neutrons as well. Alright, so does it make sense that how these two structures are possible for the same compound and how you can interconvert them with each other? Now this brings me to my next point, that if you put this molecule in X-ray crystallography machine, which gives us nearly the picture of the structure of the compound, and that's what Dr. Allen's expertise actually are in research. So the X-ray crystallography will give us a structure which is something like this, that there is a double bond there and there is not a double bond there as well, right? So it's there and it's not there as well. So somewhere between single bond and double bond you will see the structure of that compound. So this is the combined representation or the hybrid representation or the representation which is nearer to the actual structure of the compound. And how we can make it? We can simply demonstrate the new forming bond with a dashed line. So dashed line means that this bond could be there or it could not be there at the same time. That's why, we have represented it with a dashed line and not a solid line. Solid line means that this bond is there. Right. So any question? It makes sense? I think. Yeah? Are we good to go? Right, I will probably take 10 more seconds. Right. Right, so it makes sense then. Alright, that's ideal. So these are the rules that you need to keep in mind when you are dealing with resonance structures. First rule is that your Lewis structure, in case of when you have options to make multiple Lewis structure, then the structure you should go with should have as many octets as possible. Because the principle of Lewis suggests that octet makes molecule more stable. Right? That's what you read in that slide, right? So you should try to make a structure in a way that all atoms have as many octets as possible. That's principle number one. Principle number two is that it should have as many bonds as possible. So when this applies, you will go with this. When this does not apply, then you will move to this. When this applies, perfect. When this does not apply, you will go with this. We will look at the example and then you will know what I'm saying. When this is applied, perfect. When this is not applied, then you will go with that. So it's not that all these four should be followed in every example, but maybe one of them would be, working in some of the structure and the other one would be working in other. But please keep them in mind that first condition is that it should have as many octets, second is as many bonds, third is has the negative charge on most electronegativity atom because it makes sense. Electronegativity would like to pull electrons. Electrons are negatively charged, so the negative charge should be present on more electronegative atom. Finally, has as little charge separation as possible. We will look at examples and it will all make sense. So, how you can decide that between two possible Lewis structure, which one is the major contributor to the actual structure and which one is the minor contributor to the actual structure by utilizing those four rules that we just seen. So in this Lewis structure, we have all octets and no charge separation, right? 1, 2, 3, 4. 4 times 2 is 8, so oxygen's octet is complete. 1, 2, 3, 4. Carbon's octet is also complete. So that's why this structure would be favorable. And that's why this will contribute to the actual structure more than the other structure. That's why we like to call it major contributor, and this as minor contributor. And this contribution is to what? To the actual structure, which we will get experimentally using the X-ray crystallography machine. In theory, how would we know? We wouldn't know. This is also right, this is also right, but this one makes more sense. Why? Because based on those four principles. So if in exam or in any, place you are asked to draw the Lewis structure, which one you will draw? The major contributor. In exam you would be asked, or you could be asked, that draw the major and minor contributors as well, or draw all possible Lewis structures. Then you can think about making one. But if you are only asked to draw one, just go always with the major contributor. Make sense, right? We don't want you to do extra work, but if it gives extra marks in exam, then why not? Right? Another example where we will probably see the next rule. So the next rule was, when both resonant forms obey octet rule, the major contributor is the one with the negative charge on most electronegative atom. So here we have negative charge on nitrogen, but here we have negative charge on oxygen. Now this is trivial information that oxygen is more electronegative than nitrogen. That's why the first structure should be the major contributor. Right? Correct? Now let's talk about this example. So in this example, some other rule is being applied, which is one of those four. What is happening here? That here we don't have any charge separation, while here we have this charge separation. Right? So which one would be major? Which one would be minor? So no charges, perfect. Charge separation, not so good. Correct? Final example. This was a problem, but I guess I will just show you the answer. You can probably take your time when you're doing your homework. And I'm not giving you homework, but you will review this slide when you have your own time, and at that time you can solve them with your own help. So here, this is actually an exact question from one of the previous year's exams. So you can expect a question like this from this topic. What is the question? That draw the important resonance forms for this ion, which is CH3OCH2 with the plus charge. Indicate which structure is the major and minor contributor, or whether they would have the same energy. So you see that how descriptive the question is. You cannot simply draw one structure in this case, because it is asked that you have to draw major and minor both. So that was what I was saying, that you have to read questions carefully and answer according to the questions. If you only draw one in this case, you will not get 2 points. Right? So that's your minor contributor, and the other one is your major contributor because of the octet rules. Right? Another problem, another solution. Right? I mean, the explanation is also there, so you wouldn't have any problem later, even if you want to do that later. Yeah? Final part, the second last part of today's lecture would be to look at other type of structures. So far we have looked at Lewis structures, right? So Lewis structure is quite a handful. You have to draw dots, then you have to convert them in lines. Sometimes that lines are very useful, but sometimes they are not that useful because it does not add any additional value. How? Because in some cases we can simply write them just like that. We don't need to always draw these lines, because it is understood that this carbon has 3 hydrogen, So these 3 hydrogen will be, having covalent bonds just like that. Why do we know this? Because we know that carbon can make 4 bonds. So one of that bond will be with other carbon. So we don't need to draw it. And then the rest of the 3 bonds will be the 3 hydrogens. So CH3, CH3 actually tells better story than this drawing. Why? Because this is condensed and it's logical. There's no confusion in someone's mind when they look at this structure that, yeah, this would look like that. But who has all the time in the world to draw these lines? So in a lot of textbooks, as well as for the sake of this course, you will be looking at condensed form structures a lot. So I know that some of you may have practiced about one of the form and not the other form. And then there are many, many forms which we will look in next slides as well. But please train your mind a little bit to simplify things as well. Right? So when not needed, you don't need to draw the lines and the curves and all. You can simply condense the structure together. There would be no point deduction or point addition for any one of these over the other in your exam. That's what I mean. Yeah? Right. So no problem, right? In some cases, we can put parentheses as well. We will look at the examples. Yeah? So when you have extra indication, for example in this case, this bromine, we don't know if it is attached to which carbon, if we don't draw it. If you write bromine at the end, we wouldn't know that where it is in all 4 carbons. So in that case, we have to specify that where bromine is. But do we need this line? Actually, we don't. You can just write bromine here in the middle, and that will tell that it is at number 3. But then, it could also be on number 4, if we put that in the middle. So in this case, we do actually need to draw bromine. So use your judgment that when we need and when we don't need based on if it simplifies the structure or if it complicates the structure. That's the only rule for condensed form. So this is kind of a shorthand writing or shorthand typing.
It says PR text, so you can get the bromine with that one C.
The first and last, is it left or right? That's what you're saying.
No, CNH.
Between C and H here. Can. But then H are simply not there. You will see that in other form we actually omit H. So H are not that important, to be honest. We will see in the condensed form, which is I think next on the slide, or the line angle drawing, that we simply omit H. H are there, right? H are there to fulfill the valency of carbon. That's their reason. When you will be drawing the structure, H are not that important. Yeah? Right, in this case, we have double bond. So double bond needs to be drawn because how else will you learn? Especially when they are with heteroatom. So in most of the compounds, we will only have carbon, hydrogen, oxygen and nitrogen, right? So out of all the elements, carbon and hydrogen are simply carbon and hydrogen, while all other atoms are also referred sometimes as heteroatoms for some reason. So that's a term from the text that carbon and hydrogen are carbon and hydrogen, and all other elements can be referred to as heteroatoms, which are not carbon or not hydrogen. So that's what I was saying, that hydrogen is kind of, understood. So carbon is the core of molecule because organic compound, while the other atoms could be simply called heteroatoms. It could be oxygen, could be nitrogen, phosphorus or whatever. Right? So here we have example of parentheses when we don't need to draw the same thing over and over again. Then what we do here is that 1, 2, 3, 4. We have 4 same things, right? So CH2 parenthesis 4. this is making our life easier, right? That's the purpose. But I totally understand that if all your practice from your childhood is about this, I don't mind. But these are just the options. And once you will go through different texts from different books, sometimes you will see this structure, sometimes you will see that structure. You should be able to realize that, yeah, okay, this is same or not, or this is different or not. This is the whole purpose of showing you these examples, right? My favorite is the upcoming one, which is this one, line angle drawing. You just omit everything, you draw a zigzag, and the corner of these zigzags are carbons, and then as many hydrogen as it needs. So imagine that if you are working with organic chemistry and you are doing a lot of long equations and reactions, how easier would this be? Right? So this is my favorite by far. It makes sense? All edges are carbons. Only this you need to remember. So we have this carbon here. The hydrogens. At the corner, it will be 3 hydrogens. In the middle, it will be 2 hydrogens. Right? 2 hydrogens. 3 hydrogens and then carbon. Right? So this is called line angle drawing. A lot of modern text for organic chemistry is utilizing this to save ink, to save pain of your wrist, everything. But again, please do not be discouraged if you cannot understand this right away. This comes with practice. If you feel that you will make some mistakes in utilizing this form, that is fine as well. Yeah. This is also sometimes called skeletal structure or stick figure. Nitrogen, oxygen, or all the heteroatoms, they must be drawn. Carbon and hydrogens, you don't need to draw. All other atoms, you really need to draw. Right, so this is how the numbering, never mind, we will do this later when we are doing the IUPAC nomenclature. But here is an example, just forget the numbering, but you see that you have so much cluster of bonds here, and then what you need here is actually just this bond and all the zigzags. This hydrogen is also not that important. You can omit that. But yeah, this CO bond O is super important. Because what else would there be? If this carbon has 1, 2, 3 bonds already, then the fourth one would be hydrogen. So you actually don't need this as well. C double bond O is perfect. Forget about numbering for now. Don't be confused with it. We will do the nomenclature, proper IUPAC nomenclature of every classes of compound once we are doing that. So today is not that day. Yeah? Right, this brings me to the final topic for today, isomerism. Have you heard of this term before? Yes, right? I heard some no as well. No, everyone said yes, is it? Okay. I thought that somebody said no as well. So isomers are the compounds which have same, which formula? Molecular formula, but different structure, right? So mainly we can have constitutional isomer or stereoisomer. Constitutional isomer meaning different arrangement, right? Different linkages. While stereoisomer would mean different orientation in terms of their space management, right? So stereoisomers is mainly about 3D aspect of the structure. While constitutional isomer meaning simply about their arrangement. If you take this and put this way, what will happen? If you take this and put it with that, what will happen? So that is covered in constitutional isomers. While if you talk about the orientation in the space, the 3D aspect of the structure, that is mainly covered in a stereoisomer. The term stereo actually means 3D, or the space. While constitution means to constitute, I guess, so it comes from their composition. Yeah? We will look at a few examples and you will probably remember a lot. So all of these three compounds are pentane. If you don't know their names yet, don't worry, we will study alkanes in probably our next class or the next class. But the name of these compounds are all pentane, as you can see. Right? But there is something before pentane that is used to tell that these pentanes are not same, they are different. And how they are different? They are different based on their structures. Right? So there we have 5 carbons all in one line. Here we have one branch. Right? We have 4 carbons in one line and then we have one branch. Here we have only 3 carbons in one line and then we have 2 branches. So you could clearly see that all these 3 structures are different from each other, right? So that's why they are what type of isomers? Constitutional isomers, right? Another example of constitutional isomer are these two, or these two. So here the arrangement between carbon, oxygen and carbon is different, and here carbon, carbon, oxygen. So this and this molecule, both of them have the exact same molecular formula, but their structure has made them in 2 different classes of compound. And that's why their name is also quite different. Like in previous example, all of them were pentane, right? But here this is called dimethyl ether and this is called ethanol. The reason for that is that they are from different family now. And those families are called functional groups. And based on different functional groups, in some texts, you can also find their definition to be called as functional group isomers. Now, what is a functional group? This detail we will definitely cover in our next class. But to give you the idea is this, that functional groups are different chemical families of organic compounds. One of the family is called ether, and the other family is called alcohol. So this alcohol is called ethanol for some reason, forget about the name. But this is a different functional group. Why? Because this group is the core of the alcohol functional group. While in this molecule, this group is the core of what we call as ether group. Too much detail. You don't need to know this for now. But you can appreciate and tell that these two are really different in terms of their arrangement, right? Again, these two, here we have this arrangement between carbon and oxygen, while here we have this arrangement between carbon and oxygen. So these two are 2 different functional groups. What their names are, we are not interested at this point, but they are from 2 different families of compounds altogether. So that's why they are also sometimes called functional group isomers. Right? So these 2 are examples of constitutional isomers. There are other examples as well, but we don't need to go in a lot of details of these. Let's look at some examples of stereoisomers, and with that we will conclude our today's chapter 1. So very common example of stereoisomer is called geometric isomers or cis-trans isomers. So remember, by definition, stereoisomers are about the orientation of molecules in this space, right? So this alkene and this alkene, the difference between them is what? That here we have these 2 groups on the same side of carbon-carbon double bond, while here we have these 2 groups at the opposite side of the carbon-carbon double bond, right? Here, the both green balls are on the upper side of the carbon-carbon double bond. But here, one green ball is on the upper side and the other green ball is on the lower side. So that's why they are not same. Only because of their orientation is changed, they are 2 different molecules. And that's why they are called geometric isomers. which are a class of stereoisomers, right? Or you can also call them cis-trans isomers. Now, what is cis and what is trans? We are not going in that detail for now because we will cover this in a lot of detail when we will be studying about the alkenes. Yeah? While this molecule is also an isomer of those molecules, but here we don't have stereoisomer. So this is an example of a constitutional isomer of the same molecular formula, but these two are the examples of stereoisomers to each other. So these two are stereoisomers to each other, while this is a constitutional isomer to each of them. Does it make sense? So that is a pair, and this is just a different variant, right? That's all. Thank you so much, everyone. I would upload these two textbooks to your e-learn as well. These two are my favorite again. But of course, if you have any textbook at home, I don't know if you ever read a textbook anymore or not.